Okay, welcome back to our second screencast for the week. Our objectives for this lesson are very similar to the prior one. The only difference is now we are also going to talk about transformations of log functions. So we're going to take a little more time, walk you through how to graph transformations of log functions, and after we're done graphing the transformations, we'll go over again key features such as the domain, the range, the x and y intercepts, and the asymptotes. So here we go. As always, before you can do transformations, you have to understand what the basic graph looks like. That's what the previous screencast was about. So I'm just showing you this slide to remind you this is what the untransformed log functions should look like. They all pass through the starting point 1, 0. They all have a vertical asymptote at x equals 0. And then the function will be either increasing or decreasing based on the base of the logarithm. So those are just some things to keep in mind as we walk through these examples. Before we go over the examples, let's just clarify what the expectations are here when you draw these graphs. Log functions are reflections of exponential functions. And if you'll recall in Unit 8, we really don't have a lot of demands when it comes to graphing an exponential function. Lots of times these graphs end up with really difficult coordinates to draw accurately because of the asymptote. And so we really just look for three things when you draw these graphs. Do you have the asymptote shown in the correct spot, and is it shown as a dotted line? We show the asymptote as a dotted line because the asymptote is technically not actual points on the graph. Remember, the graph never touches the asymptote, so they don't represent any x and y values that fit in the equation. It's just a significant feature that we are often interested in knowing about. We definitely want you to show us the starting point. That is, traditionally, it's the point 1, 0, but if we transform the graph, that point is going to move possibly. So we need you to show us the starting point so that we can tell you have applied the correct horizontal and vertical translations. And then after the starting point, we really only need to have one more point so we can make sure that the graph is either increasing or decreasing at the appropriate rate. If you plot more than 2 points, that's fine, but we'll give you credit for the graph being correct if you at least have the starting point and one other point, and that's all we need. So here we go. We're going to walk you through some examples on the next few slides. Okay, so here's our first example. First of all, notice that the function you're graphing is a logarithm of base 2. On each of these examples, what I've done is I've included the graph of the untransformed function. So in black, you can see the graph of the basic log base 2 function. Now, on this example, the transformations we have, this is going to be a transformation of right 2, and this is going to be a transformation of up 1. So the first thing I would recommend you do is draw the asymptote. The asymptote is normally the y-axis, but because this graph is shifted right 2, now your asymptote is going to be over here. And the equation of that asymptote is x equals 2. If you look at the untransformed graph, there's the starting point, 1, 0. And because of the transformations, we have to move right 2 and up 1. So the new starting point should be right there. Notice that the red dot is 2 boxes to the right and 1 box above where the black dot was. Okay, we've got the asymptote, we've got the starting point. All we need is one more point. To do that, what I would recommend you do is look at the original graph, and you're always going to measure where the next point is relative to the starting point. So this new black dot that I just drew is 1 box to the right and 1 box above the starting point. So that means on my transformed graph, from the red starting point, I have to go one box to the right and one box above, and that would put me right there. So that's all you need is 2 points. You should know that the graph has to pass through that point and approach the asymptote, and then it obviously has to go through the other point and go this way. And that's all there is to it. If you are not feeling very confident, something you might want to do is just check a point on your graph. For example, that last dot that I just drew has the coordinates 4, 2. That means when y is 2, x is going to be 4. And if you would plug those values into the equation, I think you'll see that this does come out equaling 2. 4 minus 2 is 2. Log base 2 of 2 is equal to 1. And 1 plus 1 definitely equals 2. So you can see that that point checks out. As far as the domain of this graph is going to be x is greater than 2 because we only have points that are to the right. So I'm going to try to squeeze that in over here. The domain is x is greater than 2. The range of every log function is always all real numbers, so you can write that maybe using set notation, or you could use any format you like, really. The x-intercept, if you look at this graph, the x-intercept is some point between 2 and 3. It's hard to say exactly where that is, so we typically wouldn't ask you to identify this x-intercept because the coordinate is not a nice round number. The y-intercept, if you look at this graph, you'll see that there is no y-intercept because the graph only goes to the right of the asymptote. So for the y-intercept, you could say that the intercept does not exist, or sometimes we abbreviate that with DNE for does not exist. So there are all the key features of our first example. Here's our next example. This time it is base 1/2. So again, I'm showing you in black the untransformed graph. Notice it still passes through the starting point 1, 0. Also notice because the base is less than 1, this graph is decreasing. For transformations, this time we are going to go left 2 and down 4. So again, I would start by drawing the asymptote, and the asymptote has shifted over here now. The equation is now x equals -2. The starting point shifts from the black dot, it's going to shift left 2 and down 4, which means now the starting point is here. Again, look at the original graph. The next dot, the next point that has integer coordinates would be right 1 and down 1 from the starting point. So on my transformed graph, if I just go right 1 and down 1 from the new starting point, that's going to be the point on my new graph. And now I can draw in the graph. There it is approaching the asymptote, and there it is passing through that other point. And there's your graph. This time the domain is going to be x is greater than -2. Again, the range is all real numbers. This time I'll write it with interval notation. The x-intercept, once again, is not a nice round number. You can see it's some point between -1 and -2. This time the y-intercept, though, does have a nice round number. So you can see from this graph that the y-intercept is -5. And there are the key features of the second example. Okay, for our third example, this time we're using a log base 4. We have a transformation that is left 3 and up 1. And this time we have a dilation. I hope you recognize that that is a vertical dilation, and this graph is going to be 2 times as tall. So we'll talk about the dilation in just a second. So there's our normal starting point. Start with the asymptote. If you go left 3, this is where the asymptote should be now. Equation of that asymptote is x equals -3. Take the original starting point, move it left 3 and up 1, and now it's going to be right there. Now, the dilation does not affect the starting point. Let's talk about the dilation. You have to realize that the starting point, since it's on the x-axis, it has a height of 0. When you dilate, if you want to be twice as tall, 2 times 0 is still 0. So dilations do not affect the starting point. The only thing that affects the starting point are the translations. So we have to move the starting point left 3 and up 1, but the dilation doesn't do anything to it. But where the dilation does come in is when we try to plot our second point. Looking at the original graph, here is the next point that has integer coordinates. Notice that that black dot is 3 boxes to the right and 1 box above the starting point. So when it comes to doing a dilation, what we want you to do is we want you to think of the height as relative to the starting point. In other words, this dot was 1 unit above the starting point. Because of the dilation, we have to double the height. So that means the black dot will now be, it'll still be 3 units to the right, but instead of being 1 unit above, it's going to be 2 units above the starting point. And that's because we made it twice as tall. So this is how you have to do dilations with logarithms. Your height is measured relative to the starting point. So there's the starting point. The graph approaches the asymptote, and then it goes through the other point. And there's your function. Your domain is going to be x is greater than -3, range always all real numbers. X-intercept, once again, is not a number that we can tell easily. It's something between -2 and -3. The y-intercept also cannot be seen easily. The y-intercept appears to be some number between 2 and 3. So on this particular graph, we can't really determine the x or the y-intercept. But we do have the equation of the asymptote, which is x equals -3. So on to our last example. Okay, this time we're doing log base 4. As far as transformations go, we have a transformation that is right 1 and a transformation that is down 3. And this time we have a reflection, and that is a vertical reflection. So, as usual, we're going to start with the asymptote. The asymptote should be right 1. Sorry, I didn't do the best job of drawing that asymptote. The normal starting point is at 1, 0. Because of the transformations, we are going to move the starting point right 1 and down 3, which means now it should be right here. Now, once again, just like with dilations, when it comes to reflections, I want you to look at this black dot. Relative to the starting point, it's 2 units to the right, but it's 1 unit above the starting point. Because of the reflection, Instead of being above the starting point, now the point should be below the starting point. So that second black dot, you're going to move it 1 unit to the right and 3 units down. But because of the reflection, it's going to be below the starting point, not above the starting point. So notice when you look at the 2 black dots, from the starting point, you go right to up 1, but when you look at the red dots, you go right to down 1, and that's because of the reflection. So also because of the reflection, now your asymptote is going up instead of down, and the rest of the graph goes this way. Our domain is x is greater than 1. The range, again, all real numbers. Once again, the x-intercept we can't really determine. It's something between 1 and 2. And once again, the y-intercept does not exist. This graph, because of the asymptote, never crosses the y-intercept. So there's your examples of graphing transformations and identifying key features. And hopefully you're starting to get some idea of how to go about doing this. That wraps it up for our lesson. I hope you feel like we covered all these objectives here. We talked about all the different types of transformations, horizontal and vertical translations, dilations, reflections, and after transforming the graph, we identified all of the key features. The only thing left now is for you to practice and check your understanding. To do that, we want you to go into It's Learning, find the assignment called Graphing Transformations of Log Functions. This is similar to the assignment you did before on graphing exponential functions. You're going to graph 3 functions. You're going to have to draw them on graph paper, or you can draw them on a Microsoft Whiteboard. However you do it, you're going to have to upload your graphs into It's Learning. So if you draw them by hand, take a picture. If you do them on Whiteboard, upload the JPEG file or the PNG file. Please make sure you upload a file format that I can read. I cannot look at HEIC files. Some of you guys were saving your work in a file format that I could not open. And the other thing I wanted to say is, after you upload your assignment, make sure you're checking for comments back from me. If there's something wrong with your graphs, I will send you a message back through It's Learning, and I'm going to expect you to correct the mistakes before I give you credit for the assignment. So that's it for this week. Good luck with the assignment, and send me an email or post to the discussion board if you have any questions. Good luck.